Hey everyone, and welcome to another CTF Reddit video. In today's video, I'm going to be covering two elliptic curve challenges as part of JerseyCTF. The challenges aren't really like security or exploitation challenges, they were more of conceptual challenges, really just testing your understanding of do you know what elliptic curve cryptography is, and can you answer some basic questions about it. I'm pretty much just going to be like, this is the bare minimum, what you need to know to solve the challenges. If you really want to learn more about the subject, I highly recommend checking out CryptoHack. They have a bunch of challenges. This is the website. Really just an amazing resource. But anyways, back to the challenge. So there were two different challenges. The first one was holy-hEECk with ECC in there. And so they give us a bunch of description. Basically, at the very end, we can see the flag format is JerseyCTF and a point. So that's interesting. And they give us some information here. So if we kind of peel back the layers, there's a couple interesting things in this challenge. It says Anna's private key is 165. Simon's private key is 152. We're given a curve. We're given a field. We'll read all of this in a second, but this tells us how to generate a generator point. And our goal is to figure out the shared secret. And in this case, a shared secret is a point. So this was challenge one. If you know elliptic curve cryptography, this challenge is very easy, but if you don't, this seems like a lot. This challenge only had 12 solves, and I'm guessing really it's just like I think most people aren't familiar with it, and so it seems kind of scary. So in this video, I'm kind of assuming people are at least familiar with like RSA or some other crypto primitives, and I'm assuming that they're not too familiar with elliptic curve, and so that's kind of the introduction. So what does all this information mean? Well, when we deal with elliptic curve cryptography, compared to some of the other crypto schemes, there's a lot of agreement that has to happen before, and people need to agree on a couple of different things. One of those things that people agree on is the specific curve, and so this is like the mathematical arena that we're going to be doing our cryptography in. And so the arena for this challenge is this curve, which is y squared is equal to x cubed plus 18x plus 9. Because the numbers are so small, we already know that this is not like a real crypto system, this is like a play one. Like normally these numbers would be way bigger, and it is important if you're doing real cryptography to like pick a real strong curve. Obviously since this is a play example, that doesn't really matter too much. So this is the curve we're going to be dealing with. And another like mathematical arena thing is we're also going to be dealing with a finite field. And so that's what this mod 8011 means. And so for like the non-cryptographers and non-mathematical people, this just means that every operation we do, we need to mod it by 8011. Really, it's called a finite field or a Galois field. But all it really means is no number can be bigger than 811. Like anytime something wraps around, we're just going to subtract 811 a couple of times until we get back to a number in between those bounds. Cool. So we have a curve. We have our equation that we're dealing with. Again, this is not secret or anything, it's just every party needs to agree with on this curve before we start, and we're dealing with some sort of field. So you know everything is mod 8011. Normally when you do cryptography or elliptic curve cryptography, you're also going to agree on a generator point. What made this challenge interesting is we're actually going to have to determine the generator point. But before I talk about generator points, let's talk about what this math symbols mean. So if you watch other videos on elliptic curve cryptography, and I recommend you do, like again, I'm not going to give a great introduction to it, but they usually start out with like drawing some curve like this. And this equation might look like this curve, it might not. And they show like, you know, you can take points on this curve, and they define some like point operation, like you can add 2 points and maybe you'll get a different point, and you can draw lines and stuff. I personally don't really, I mean, it's a good intuition. I don't really like that. I think when you're dealing with one of these mod fields, that's just not what the curve looks like. I think instead you should think of this curve as just like a collection of points. And like I wouldn't even think about that type of curve. Really here we have like a y and an x. And it's just a standard math equation. So if you were to solve it for a bunch of different points, you might get the point like 5, 13. There might be a, 7, 2000. I don't know, like 500, 300, at the end of the day, there's only a set amount of points that solve this equation because we're in this finite field, because we're limited here. And it's when you actually plot these out, they're not going to look like this. Really, you're going to have like a point here, 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 here, all over the place. There's going to be a couple of thousand different points, and those are the only solutions to this particular curve. Cool. In elliptic curve, like there's no magic when it comes to elliptic curve cryptography. Really, it's just a human invention, and some very smart mathematicians, they defined an operation for adding 2 points together. Again, there's no magic. It's just an algorithm. You follow the algorithm, and given 2 points, you can get a third point. And it's just something everyone agrees on how we should do things. There's probably some like mathematical reason why it's this particular algorithm, but who knows? It just, as a CTF player, I personally don't really care. I just know that given 2 points, we can generate a third point. And it can even be two of the same points. Like we can add this point with itself, and maybe the result of adding, I'll do it like this. Maybe the result of adding this point with itself is this point. The algorithm for adding points together isn't terribly complex, but it's not like super trivial either. Like there is a couple of steps for doing it. But anyways, so there's an algorithm for adding this point, and maybe you'll get this point. And there's an algorithm for adding, this point. It's the same algorithm for this point, and maybe you get this point. But what's important is like, as you add these different points, really you're just going to jump over like all over the place on this map. Every once in a while, you'll return back to the same point. So let's say we're continuously adding this point to itself. So if you add it to itself once, you get this point. Then if you add it again to this point, you get this point. Let me actually use the highlighter. So if you add this point and this point, you get this point. And if you add this point and this point, you get this point. And if you add this point and this point, you get this point. And you continue. It's very possible, and it is actually, it's guaranteed. Eventually, you're going to wrap back around. And this is super important in elliptic curve cryptography, and it's very important to this text that we'll read about in a second. And so, like I said, eventually it's going to loop back to the same point. And then from there, it's just going to continue in the circle, and it's just going to repeat over and over. And the number that characterizes how many steps you take before you come back is called the order. And so this one would have order 1, 2, 3, 4, 5, 6, 7. So we have a order 7. And so if we were to call this point our generator, this generator point would have order 7. So cool. And I think that's pretty much all we need to know for this challenge. So just to recap, within this elliptic curve scheme, we're given a curve, public information. It's this curve up here. Very standard sort of curve. Again, the numbers are small. Normally the numbers would be much bigger. We have a finite field, which is this number. And so everything's going to be mod 8011. Then there's usually a generator point, but in this challenge we're going to generate the generator point. And I guess the last thing is when we think about how this elliptic curve cryptography system works, it mentioned that there were 2 private keys. So Anna has a private key and Simon has a private key. So there's a bunch of different ways you can use elliptic curve cryptography, but this is probably the most common, I would guess. And the goal when you use this system is for 2 people who have never spoken to each other, they can agree on a secret even if the whole world is listening to their conversation. So Anna and Simon could be, in the middle of a train station with, thousands of eavesdroppers, and none of those people, as long as they follow this protocol, and if they've never spoken to each other before, they can still agree on a secret that only the 2 of them would know. And when you do this elliptic curve cryptography thing, the secret that you get out of it is just a point. And so you can take up the hash of that point or something and generate an AS key and then start, like a full-blown conversation, or you can do whatever you want. But as soon as you have some like private material that only the 2 of you guys, or the 2 of those people know, then you have a secure communication. Okay, the way that works though, it's very similar. I think this is like the Diffie-Hellman scheme of elliptic curve cryptography. But basically what's going to happen is we're going to have Alice. Oh, sorry, this is not Alice, this is Anna. We have Anna. We have Simon. They're going to agree on some curve. So we have that curve equation. They're going to agree on some field, which for us, this is 8011. And they're also going to agree on a generator point. And again, this is just some point that's on the curve. And it's just public information. It's agreed on before. We want that point to have specific properties, again, which we'll talk about in a second, because this is like the core of this particular problem. But normally it's just given. We pick a generator point, and that's what's used. What's going to happen when they want to do this scheme is Anna's going to generate a private number. We'll call this one A, and this private number is just any number within the field. So normally this field would be much bigger, less than 8,000. But so Anna's just going to pick a number between 0 and 8,000, and Simon's going to do the same, and we'll call this S, I guess. So we have A and S, and these are private numbers. Anna is then going to generate A times G. And so again, like if this was our G point up here, Anna's going to take this point and multiply it all the way around a times. So if her number was 5, she'd go 1, 2, 3, 4, 5. So this would be the number that she would use, and eventually she's going to send that to Simon. Bob's going to do a very, or sorry, not Bob, Simon's going to do a very similar thing. He's going to do S times G. So, he's going to multiply this point by, a whole bunch of things, and eventually, he'll get some point back. They're going to send each other. This is the next challenge. I'll move that out of the way. They're going to send these numbers to each other, these points to each other. And what they're going to do at that point is Anna's then going to multiply, she just received S times G. She's going to multiply that by A. So at the end, she's going to have A times G. And Simon's going to receive A times G, and then he's going to calculate S times A times G. The way the mathematics works out, these numbers are the same. Just, I guess, one of the properties of the way we define elliptic curve addition and multiplication, these numbers will be the same. What's also cool is any eavesdropper, so any eavesdropper can listen on this channel anytime information is sent back and forth. The eavesdropper will know what S times G is and A times G is, but they can't actually recover what the original A and S were, which is pretty cool. I think you'll have to read some other resources to really get an understanding of it, but I mean, like the simple interpretation is like it's very easy to go forward along this chain, but it's very hard to go backwards along this chain. You pretty much you just have to brute force it. So anyways, that is the elliptic curve scheme, I guess, that we're kind of playing with. So this challenge, now that we have the base out of the way, we can actually read what this challenge is asking us. And so that was this description right here. So before heading off to perform his heist, RB crackled and told blah, 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 blah. The secret key can be generated from the elliptic curve algorithm using a perfect number generator point on the curve with the greatest x coordinate out of 2 y coordinate, blah, blah, blah is the lower coordinate. Cool. So a little bit strange. Again, this is non-standard stuff. I actually had to ask during the competition what a perfect generator point was. I haven't heard that word before, and if you Google for it, it was the only place I could find it was on an NJIT homework assignment that a bunch of people were sharing answers for online, like with Chegg and all those other websites. So I don't think this is a standard term, but once he described it, or the challenge author described it, I mean, it makes sense. Basically, what this is asking us to do is we need to calculate a generator point, find a generator point that has the maximal order possible. So the maximal order possible would be if, just like what is the maximum number of points you can hit on this particular curve. Like I said, there's going to be a bunch of these cycles, like these little orders. We had one here, was this like order 7 or something like that. It's possible that if we picked this point instead, it might have order like 200. And it's possible if we picked this one, it might have order like 8,000. And that really means that there's 8,000 points that this will hit before it cycles back onto itself. So to solve this, we need to figure out what the maximal order is, and we need to find the highest x point. So this is our x-axis. We need to find the highest x point that is a member of that high order curve. There's probably a lot of advanced mathematics that go into determining that stuff, but we're going to be using a tool called Sage, and Sage is going to do all of the heavy lifting for us. If you're not familiar with Sage, it's like a mathematical toolbox. It's built on top of Python, but it does, it just has a lot of cryptography and mathematical stuff built in, and it makes doing this stuff super easy. So first, let's start Sage. I probably actually should have done this earlier. It's very slow. If you don't want to install Sage on your system, you can also do it in a Docker container. There's a whole bunch. But if you've never seen Sage before, welcome to Sage. Again, Sage is really built for mathematicians. It's a little bit hard going through the docs sometimes and searching for simple things. But it is what it is. Again, it's built for real mathematicians, not the casual CTF player. So first thing we're going to do is we're going to define a field, and we can see I already have it here. So this is a Galois field. You can also use finite field. It's the same thing. So we have our field, and again, you see it's a very Python-like sort of interface. Then we're going to define our curve. We're going to say E is, it already saved everything, so E is equal to elliptic curve. So we define our field and those two parameters. So if we remember the equation, let me go back. This was the equation we're trying to use right here. The two parameters that are interesting is this 18 and this 9. And so those are the two, values that determine this curve. Let's go back here. So now we have a E. So like I said, there's a whole bunch of points on here. A way to get points, there's probably different ways to get points, is there's this tool called LiftX. Oh, we already have it. So if I wanted to know what a point, anyway, this is a valid point on a curve, 1, 9, 4, 3. And so this is the x coordinate and this is the y coordinate. We could also ask for a 2, and there is no point on this curve that has a x value of 2. We can try 3. There's no 3. Oops. We can. Oh, what's going on? 3. There's no 3s. We can try 4, and there's a 4. There is a point with coordinate x equals to 4, y is equal to 5, 8, 4, 8. All right. And you can do a whole bunch of stuff with this elliptic curve stuff. I don't know like what most of this stuff means, but it's all there if you want to get fancy. One thing that Sage does for us that's super nice is, and I think makes this problem super trivial, is you can just ask what the order of this curve is. And so the order of this curve is 7, 9, 0, 2. So this is the maximal order possible on this curve. And so if we were to pick the correct point to use as our generator, it would take 7,902 additions before it cycles back on itself. But that depends on the generator point. So you can actually ask Sage for a generator point, and it says that this is a good generator point. And so this could be our base point, this is our x, and this is our y. And so then you can ask what the order of this particular point is, and it'll tell you. It's the maximal order. But there's a whole bunch of them. I mean, we could do any of them, any generator points. It's up to us to pick. I guess Sage particularly picks this one. I'm not too sure why, but Sage seems to like this as the generator point, even though there are other generator points we could use. So the problem asked for the highest x value that we could use that has the maximal order. So if we were to start at the very end, the highest x value possible is 8, 0, 1, 1. So we could generate this point, and actually we want 1, 0. There's this point. So there is a point at x value 8010, and it has a y value of 5311. We can ask what the order of this point is, and we can see it doesn't have a maximal order. So if we were to use this as our generator point, as we're multiplying the points together, it would take 3,951 operations before it returns on itself. Okay, so that's not a perfect generator, as the description said. We could try 8009. Oh, there is no point there, so that one doesn't work. So we could, keep going down. I don't know how long it's going to take. So I wrote a little for loop here. I'm just going to copy this code, but for I in range from the top, just going down a whole bunch. Try printing out the point and its order, and if its order is the same order as the maximal order possible, just stop going through the loop. So let's put this in, and it didn't do anything. Okay, sorry about that. It's working now. I guess at some point I accidentally typed in f is equal to 3 or something like that. Yeah, I don't know how this got in here. I must have messed up, but I redefined our field as Galois field 3, which doesn't make any sense. So if I redefine f is equal to our full finite field, and we run this algorithm, then it works fine. So sorry about that. But anyways, so it prints out the first one. So if we were to use an x value of 8010, we would get this as the order. If we were to use then this as our x coordinate, we would get a order of 7902. And if you remember, this was the maximal order. So if we use this as our generator point, 8008, that should work. It is the maximal x value that gives the maximal order. One thing to note is the challenge description kind of mentioned it. Sometimes there can be multiple points with the same x coordinate, and it says use the lower y coordinate. So one way to do this is we can take our elliptic curve, we're going to lift x, 800x, so we're going to get that point. But I think you can do, is it all equals true? Yeah, there are multiple points that have the x coordinate of 8008. So there's this one, and there's this one. It says use the minimal y one, which is this one, which is what lift x by default does, I guess. So we don't have to worry about that. We're just going to use this one. Cool. So now we have a generator point on the curve. If we go back to our little whiteboard here, so as part of this algorithm, Alice needs to multiply a times that generator point, then she's going to send it to Simon, and Simon's going to multiply a times g by his secret. In the challenge text, they gave us the two secrets, so we have 167 and 152. So it doesn't really matter, thanks to elliptic curve magic, it doesn't really matter what order we do it. So we can either multiply it by 167 first or 152 first, and then we multiply it by the other one, and that's all we have to do. So we're pretty much there, and thankfully the magic of Sage, it does everything for us. So we just take that point. Let's just say G is equal to this, and it was A is equal to, where did I put it? 167, and let's say S is equal to 152. So we can do A times G, and that is one of the shared points. And then if we take this, we can multiply it by S, and there we go. This is the answer. We can also do it the other way. We can do A times S times G, and we'll get back the same point. So now this is the shared secret that both parties agree on, and we're assuming that if there was an eavesdropper, there's no way that they'd be able to determine the value of this point. Although that's not true because we're dealing with such a small curve and you can brute force 8,000. But if this was a real crypto system, there would be no way for anyone else to guess this point, which is pretty cool. So anyways, this was the solution. You can just wrap this up in a JCTF. I think this was the flag format. So it'd be 7316461. Cool. So problem 1 done. For the second challenge, once you understand all that stuff, the second challenge was very easy. Let's clean some of this up. Anyways, I'm going to delete this, but we needed to, as part of this challenge, we needed to find the algorithm. I just put this paper here because this is what I actually used to find the algorithm. I'll just delete that now, though, because we don't really need it. Let's make this bigger. And let's scoot. This is the algorithm we use. Cool. So for step 2, there's a bunch of challenge description. It's not too necessary. We're going to see a couple interesting things, though. First off, I didn't realize this at first. This word right here is very important. This is the name of a very particular scheme within elliptic curve cryptography. I wasn't familiar with this scheme, and after doing some Googling, it doesn't seem to be too popular of a scheme, but it is a scheme that exists. And so we had to, the hardest part of this challenge was actually figuring out how this scheme works, because a lot of the papers just didn't really spell it out, and yeah, it doesn't matter too much. But really the hard part was just figuring out what the scheme is and how it works. We're given another curve, so this time our curve is y squared is equal to x cubed minus 43x plus 166, and we're modding over the same field. So pretty similar curve, except, it's just these two parameters are different. There's another little complication in this one. It says Hal isn't the brightest bunch, blah, blah, blah. He can't remember what is the generator. We should use the point with the highest order, and the 3 points are these. So one of these has a high generator, one has a high order. We just need to figure it out. And since we're using Sage, obviously this is trivial. We're just going to ask Sage which one has the highest order. We're also given a public key. This is, once we figure out how this very particular crypto scheme works, it just requires a public key. We're also given this private key here. Key is equal to 3, which is good. And we're also given a message, which is this point right here. And so we need to figure out what the encrypted message would be, and that is the flag format. Really, like I said, the difficulty of this challenge, elliptic curve-wise, it wasn't complex at all. The only thing was just figuring out what this Menzies-Vanstone elliptic curve protocol was. Eventually I found it in that paper that I showed a second ago. This is the algorithm. And it pretty much, we're just going to follow this, and we're just going to give it to Sage. Sage is going to do it for us. So when the sender wants to send a message, so message M, we have that. That was this. Cool. They first need to agree upon an elliptic curve with a field. We have those. And a base point G. We need to figure out what the base point G is. They gave us those 3 different base points G's, these 3. But, we can do that easily. Each party chooses a random private key. Cool. And then a blah, 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 D for A, E for B, and they're going to calculate the public key. They gave us the public key of the other person, so that's all we really need. We're not going to deal with the D for A or E for the other user. We just have the public key already. Cool. And so yeah, we have this one, I guess. Cool. Then user A is going to compute a secret K. We have this K value. By multiplying the private key by the other person's public key. So we're going to multiply K by that other private key. Then we're going to calculate this, and then we're going to calculate this. And so we're just multiplying specific points together. And so at the very end, we're going to end up with this. A point, a agreed upon point, and 2 different ciphertexts. And this is the private encrypted message that we would be sending over to Kilowog. So at this point, again, there's nothing really insightful. Keep sharing. Going on, we basically are just going to plug and chug numbers until we get the correct solution. And again, Sage is going to do all the heavy lifting for us. There really isn't too much to really think about. So if we go back, so this is the solution to the second challenge. I'm not going to type everything into Sage since we already saw it for the first challenge. I'm just going to quickly go over the solution. So we can see we're going to define another elliptic curve. I do that here. We have new curve parameters, so I put those in here. Then from there, we were given 3 different possible generator points, and we have to figure out which one has the highest order. So we just type them in, all 3 of them, and we can see the highest order was the first one with an x-coordinate of 59. Cool. From there, then we just follow that algorithm that was outlined in the paper. I really don't have anything too insightful to say here. We're just going to calculate the g point, the q point. You need to make sure it's using the correct y parameter. You just sprint it out, but it ended up picking the correct one. And then you just do the multiplication. At the very end, you're going to get out the y0, y1, and y2, although the paper called them c1 and c2, and you submit it. Like I said, really nothing too complex here. You're just following the algorithm. And yeah, that was the challenge. Overall, very cool challenges. It's nice to do some conceptual questions and make sure we really understand how things are working. If anyone has any questions, feel free to leave it below or message on Discord or email. If I said anything wrong and there's some crypto experts watching, please let me know. Put it in the comments. I'll make sure to pin it to the top. And with that, I'll see you at the next CTF. Cheers.